Hello, lazy chemists, and welcome to the lecture for hydrogen bonding. Today we're going to go ahead and go over some of the fine tunings about what's going on with hydrogen bonding so that we can go ahead and delve into it a little bit deeper here. Okay. And first we're going to go ahead and define what hydrogen bonding is. And hydrogen bonding is going to be the essential force of attraction between a hydrogen atom, okay? And it's going to be a hydrogen atom that's bonded with another type of atom, and the lone pair of another highly electronegative atom, okay? And this is going to mainly be with, lone pairs for the elements that are of much higher electronegativity. So, for instance, nitrogen, oxygen, fluorine, chlorine, all of those are going to be different things that can go ahead and, help to make a nice strong hydrogen bond. Okay? And that bond is going to be in between, the different molecules. And again, before we went ahead and said that, the reason why this one's stronger is because, with the hydrogen, it doesn't have any outside electron shell. So this side, even though it's only a partial positive, it doesn't have any shielding to it at all to shield it from, the electrons that are on the oxygen side. Therefore, since there's no shielding, it makes a real close and stronger intermolecular bond. So the distance between that bond is really small because it doesn't have that shielding in between there, okay? Those electrons can get as close as they want to that positive nucleus of the hydrogen. Okay, and that just zoomed in there. Okay, and then this is just another way of showing it here, okay? It, with a little bit more of a description that we have the hydrogen bond and it's bonding here in this case to the lone pair that's on this ammonia molecule, okay? And that lone pair and that hydrogen, are bonding, and that's going to affect a whole bunch of properties for this molecule, especially when we have a whole bunch of this molecule together, okay? That just goes further deeper into that. Okay. It does require that the two molecules that are involved in the bonding are polar. And you need to make sure that, that the molecules do have a positive end and a negative end. And that you don't have a case where it's like carbon dioxide, where even though carbon is less electronegative than oxygen, the two carbons on the outside end up canceling out each other's charge. So just make sure, that when you're looking for things that have hydrogen bonding, that it needs to be a polar molecule in order for it to even do this type of hydrogen bond. Okay? And, this here is saying the most common are oxygen, nitrogen, and fluorine. I would argue that chlorine is another common one that also participates in hydrogen bonding. Okay, and this is an example of, a large body of water where, the straight lines, the non-dashed lines are our water molecules. And as you can see, it's making links up with other molecules through this hydrogen bonding. And it's these links that are affecting water. And the reason that water ends up being, a liquid at room temperature is mainly because it does have this capability of making all of these intermolecular bonds. And, these bonds are all, fairly strong, which is why even though water is a relatively light compound, so it only weighs 18 grams per mole, that it stays a liquid at room temperature. Okay. And here's some examples that contain hydrogen bonding, and I want to go into a couple of them. We just saw the water one, that's really basic. But I wanted to go into the DNA one here. And DNA molecules, when they are pairing up with their opposite sides, so for instance, when DNA unzips and zips, it ends up making or breaking different hydrogen bonds. Okay, so in biology, when you learned about DNA, you learned that you have adenosine pairing up with thymine, or that you have guanine pairing up with cytosine. Okay, and you have the ATGC type of pairing. Well, that pairing is actually being formed by a hydrogen bond. Okay, and this image right here is, not the best, but it's actually a hydrogen bond that's going on in between these two molecules right here. And I figured that we would go ahead and show in depth here what's going on. So this image right here goes ahead and it shows, here's A and T, and in the structure of the adenine, what happens is that we have a nitrogen group right here. We have a amino group right here. And it has a hydrogen on it, and it attaches to this oxygen that's on thymine. Okay? So here we have one hydrogen bond where the hydrogen is on the adenosine side. And on this one right here, we have another amine group right here, and the thiamine is bonding with this nitrogen that's right over here on adenosine. Okay? Whereas with G and C, we actually have three options for the bond. In G, we have two amine groups, or amino groups, or we have two hydrogens that end up participating in the bonding, one with a nitrogen in the middle, one with an oxygen. And then we have another one with the carbon right up there. Okay? And so I wanted you to be able to see that bond that is actually happening there is actually the hydrogen forming a temporary bond and locking that into the DNA, which is, that's going to help DNA two things. One is, breaking that bond is going to have to be something that's intentional, okay, which is why we have the zip and unzip process. But also, because it's an intermolecular bond, it's not going to be so energetic that it's going to, essentially break the energy bank of a cell if the cell needs to unzip and then copy a length of DNA in order to make a protein or to make a new copy of DNA. Okay. Cellulose groups also interlink here with their hydrogen groups. And hydrogen fluoride is another type of compound that does it. In this case, it's just, there's a hydrogen bond between each hydrogen fluoride that causes that kind of reaction there. Okay. And this right here is the other thing that I wanted to go ahead and take a look at. And these are some of the essentially the properties here that are messed with by having hydrogen bonds in a compound. So in general, melting point, it's going to increase. So it'll take more energy in order to melt something because hydrogen bonds are strong intermolecular forces. Okay? It takes a fair amount of energy in the terms of intermolecular forces to break those. So it's going to have a high melting point. It's going to have a high boiling point. The other thing is that solubility is going to be high. And typically when we think of solubility, we think of solubility in water. But the reason that we think of solubility in water is because water is so charged and it has all those intermolecular forces that are involved in there that it's going to be able to absorb just about anything. And really, if there's any charge that water can grab onto, because it's so small, water will. And this is where our like dissolve like comes from. That nearly anything that's polar, or if it's ionic, can dissolve easily in water. Whereas things that are nonpolar only dissolve in nonpolar substances, and often they don't even dissolve all that well. And this is something that you can go ahead and try, kind of like the flip idea, okay? So you're used to putting a whole bunch of different things in water, but you could do the same thing with different oils in your house. So for instance, if you have olive oil and you have canola oil or rapeseed oil, if you mix those, what will happen is that they'll actually mix fairly well because both of them are, essentially oils. Whereas if you put oil in the water, which I hope nobody's doing that in their pasta, that's just a good way to waste your oil. But if you put oil in water, what's going to happen is that oil will sit on top because it's less dense than water, okay? And the density of liquid water is partially determined by the fact that it has all those hydrogen bonds are, pushing all of that water together. And so that affects its density, whereas the oil can be a little bit more spread out. But the oil will end up sitting on top of the water because the oil, being a polar molecule, doesn't have any charge for the water to grab onto. Therefore, it's not going to dissolve. Viscosity. This is talking about how easily this thing is going to flow or move, or the thickness of a liquid, okay? And in general, viscosity, the more polarity that are involved with a liquid, the more resistance to a flow it's going to have. Okay, because it's going to have strong intermolecular forces. Okay, so the forces are going to hold on to each other quite tightly. Okay, and keep in mind that's resistance to flow in particular, and not necessarily how quickly it flows, but resistance to flow, to changing of flow. Let's see. Oh, and then we accidentally went over density. Yeah, and I like my definition there a little bit better than this one here, because often things, when they get flowing, they want to keep flowing. So just keep that in mind there. And that's going to kind of close us out here for hydrogen bonding. The one image that I kind of want to leave you guys with is, not this one, I never liked that one, is this one right here, where we're talking about like the actual bonding between the DNA. And that's just because this is something that, if you end up going into any field with biology, or if you go into biology, knowing that this is an actual hydrogen bond holding it together, and so every time that it zips and unzips, though it might have an energy cost, it's relatively low in terms of the breaking of bonds and other things. And, while we're here, why don't we go ahead and show like ATP in structure here. Oh, that's a terrible one. All right. So while we're here, this is also one of my pet peeve, molecules, because I never really was able to learn it properly until I had the chance to, see it chemistry-wise. And ATP, now keep in mind, this is what our energy source of the cell is. The ATP, the bond that we're breaking, and the bonds that we're reforming are actually covalent bonds right here, okay? So that means that the amount of energy from one of these bonds is actually going to be a lot higher than, our hydrogen bonds right here. So I just wanted to show you that one too, that here, because these are covalent bonds that we're forming and breaking, the amount of energy that we gain from this is monumentally higher than the amount of energy it takes for this. So I just wanted you guys to understand that one as well, that even though hydrogen bonds are the strongest, it's still going to be nothing in compared to, an ATP molecule breaking apart. And that'll kind of close us down for the hydrogen bonding section for today. So I hope this explains a couple of things with hydrogen bonding. I hope that you're able to understand the breaking of DNA a little bit better. And, I hope it makes it so that, you understand this particular molecular force to the level that we need to. Until then, remember, stay lazy and don't do any more work that you don't have to.